And now for chapter 16, the last chapter of Math 3C. So this is about vectors. So suppose that this is the bottom of a river and then the water is flowing along. So here it's pretty much unimpeded, so it's flowing pretty fast. So the length of the vector tells you how fast it's going. And perhaps as it hits this, it slows down a little bit and slows down a little bit. It could be up here that the water goes a little bit faster, And then as it comes over this little ridge, what can happen is the water can then create a small circular pattern known as an eddy. So this is an important idea in both fluid dynamics and aerodynamics. Okay, anyway, when you collect all of these or you look at all of these red vectors, that's a vector field. So you're looking over a whole field and you're looking at all of the vectors. Now in general, how do you create the actual function? So let M, N, and P be functions from three-dimensional space to one-dimensional space. So in other words, for M, you plug in three numbers, it turns a little formula, it spits out one number. And then capital F is then defined by take M, and that gives you the I component, N, that gives you the J component, and then P, that gives you the last component. So that would mean that at some point X comma Y comma Z, like at this point right here, so at that point, then create the vector. So this gives you the black point, and then this gives you the red vector. Oops, vector field. And then let's look at some examples. So for example number 1, pretty much the simplest one there is, at any point X comma Y comma Z, then the vector is going to be X for the I part, Y for the J part, and Z for the K component. Or if like me, you prefer this notation, the vector is X comma Y comma Z. So what if we graphed that in 3 dimensions? So at the point 0, 0, 0, you plug in 0, 0, 0, the vector is going to be 0, 0, 0. So it's that vector. Then what if you went out to where X is a 1? So 1, 0, 0. That means the vector is going to be 1, 0, 0. So that vector looks like this. And if you went out 1 on the y-axis, you would get this vector. And then 1 on the z-axis, it would be going up like this. Then what if you picked a point that is like right here? So if this was the point, go over by 1 in the x direction, go over by 1 in the y direction, and then go up to z, so something like that. Then at this point, the vector, so it would be going in this direction, the same direction, but it'd be this vector, and it would be a little bit longer because its numbers would be bigger. And then if you went out farther, it would make a vector that's even longer. And everywhere you go, there's vectors that are going out. Okay, how about example number 2? So with example number 2, I got excited and I started working on it, but it's going to do the opposite. So instead of the vectors going out, they're going to be going in. And then also divide by the length of x comma y comma z. and then even cube that. Or in other words, if this is the vector r, this is negative of r, and then r, its length, gets cubed. So what that would look like is, if the numbers for r are very big, then you're going to be dividing by a big number. And also the negative means the vectors are going to be pointing in towards the origin. So when the numbers are really big, like you're way out here, then you're going to be divided by a big number, so it's going to make just a little vector. And then as you get closer, it's going to make a bigger vector, and then closer, an even bigger vector. And that happens from all directions. So the farther you go out, the smaller the vector is. The closer you are, the bigger the vector is. And they're all pointing towards the origin. You know what that is? That's the pull of gravity. So this could be the sun, and if you're really close to the sun, then the pull of gravity is going to be very strong. But if you're way out here, then the sun's going to tug on you a little bit, but not that much. And if you're way over here, then it's barely going to pull on you. Next, example number 3. Suppose that you have a function. This is not a vector. It's just the function x squared plus y squared plus z squared. That's not even a vector function. It's just a regular old function. So how do we get a vector function out of that? Oh yeah, you're right. What about the gradient? So the gradient is the vector where you take the derivative with respect to x, you take the derivative with respect to y, and you take the derivative with respect to z. And now we've just created a vector field. So then we'll call it capital F. So in this section, capital F means the vector, and lowercase f means that it's just a regular function. So then capital F in this case will be derivative with respect to x is 2x, derivative with respect to y is 2y, and the derivative with respect to z is 2z. Now with x squared plus y squared and z squared all added together, that basically makes a sphere. Where the center is 0, 0, 0. So there's the origin. And then, like with example number 1, this one was x comma y comma z, and it has the vectors going out like this. So if you're at some point right here, then the vector is going to go in this direction, but it's going to start at this point, so it's going to go like this. And it's going to be perpendicular to the surface of the sphere. So if you're at this point, then go along this line and then make that vector, and it's going to be perpendicular. And then this is important in applications and things like that. So if this was a water balloon that was filled with warm water, then as the heat escapes, it's going to go through the membrane or go through the rubber of the water balloon. And as the heat escapes, it's going to go perpendicular to the surface as it escapes. Then, for example, number 4, suppose that the function is x plus y gets squared over 2. So that's the regular function. That's not a vector. Then create a vector field by doing the gradient. So the derivative with respect to x. the 2 would go down in front and multiply. It would cancel the 2. It would leave x plus y. And then when you take the derivative with respect to y, the same thing would happen. The 2 would go down in front and multiply. And so the vector field would be x plus y, comma, x plus y. So what do those vectors look like? So this has just got x and y, so I could do that in 2 dimensions. Here's x and y. And then notice that if you look at this line right here, this is the line where y equals negative x. And if y is equal to negative x, then negative x and positive x will be 0. Negative x and positive x will be 0. So all along here, it creates vectors that are just 0. Then what if you were at one point like 1, comma 1? So this is 1 and 1. So 1 and 1 means the vector would be 2, 2. So 2, 2 goes in the same direction as 1, 1, but it would be a little bit longer. And then if you're at 2, comma 0, so if you're at this point right here, then 2, 0, 2, 0, that's the vector 2, 2, which actually is parallel to that one. And if you were at 0, 2, it would create the same vector, parallel, and the same length. And then what if you were, let's say, at negative 2, negative 1? So a negative 2 and negative 1 is negative 3, negative 3. So negative 3, negative 3. So it's going to go like this direction, but I have to do that from this point. So negative 3, negative 3 would be about like this. So it would go about like that. Okay, then on to the next idea. So you can be given a function and then you can create a vector field by doing the gradient. Well, is it then true that you could work backwards? If you were given the gradient, could you work backwards and find out what the original function was? So given that the gradient of f creates a vector field, can you work backwards and find out what the original function was? So through the magic of paper, I can go like this. So there's the question. If you know what the gradient is, then what's underneath the paper? Oh yeah, it's that one. But let's try it with a different example. I believe this is number 5. Example number 5. So suppose that the gradient of f is equal to this vector field. It's got e to the x, it's got sine of y, and it's got z squared. Then find the original function f. So it means that somebody took the derivative with respect to x and they got e to the x as the answer. Somebody took the derivative with respect to y and they got sine of y as their answer. And also they took the derivative with respect to z and they got z squared. So if the derivative with respect to x is e to the x, then what's the original function? Well, if that's the derivative, then we need to integrate or find the antiderivative. And the antiderivative of e to the x is e to the x. And when you do antiderivatives, of course, there's plus a constant. Now in Math 3a and 3b, a constant would be an actual number. But in Math 3c, anything that has a y or a z in it, that's considered to be a constant when you're taking the derivative with respect to x. So this c could actually have something that's got a y in it, a z in it, or a number. Then move on to the derivative with respect to y turned out to be sine of y. So then do the antiderivative, and the antiderivative of sine is negative cosine of y, and then plus a constant. Well, because I already used the letter c, maybe I should be more specific. That could be c number 1, and this could be c number 2. And then it's this guy's turn. The derivative with respect to z was z squared. Then find the antiderivative. So the antiderivative of z squared will be z cubed over 3, and then plus a constant. Now put all three of these together because they all tell you what f has to have. So f has to have an e to the x. It also has to have minus cosine of y. And it also has to have z cubed over 3. And if there is a number at the end, like plus 12, that would be fine also. So if you find the gradient of this, you'll find out it equals that. Now that idea is so important that it even has its own definition. So a vector field, in general we call that capital F, is conservative. If f is equal to the gradient of some function. So if you want to know if f is conservative, then you actually have to work backwards like we did right here and find out what the f is so that the gradient of little f is equal to capital F. Now the reason for this word conservative means that you conserve. So if I wanted to conserve gasoline, then I could stay in my house and not drive my truck. Or another way to look at it is, if I was going to drive from point A to point B. Well, I could do it like this, go over here, and then go over here, and then go over here, and then eventually I get to B. But did I conserve my energy by doing that? No, I expended a lot of extra gas or a lot of extra energy by doing all of this crazy whoop down, up, down, up, down. It would have been better if I just made a straight line and went straight across. Well, in the upcoming sections, we're going to be doing what are called line integrals. So, and don't let the word line fool you, it's curve integral. So you integrate the function and you go along this red curve. And then that takes a lot of extra work. It would have been easier to just integrate along a straight line from A to B. And you are allowed to do that. In other words, you'll get the same answer whether you do the red one or you just do the black one. You'll get the same answer when you integrate as long as it's conservative. Now you may be thinking, wait a second, that does not make sense. How could you get the same answer going straight as when you go up, down, up, down, up, down? Well, I'll show you an example. Suppose that at one point in time, whenever, time A, you buy Apple stock for $100 a share. Sometime in the future, you sell Apple stock for $200 a share. You just doubled your money. So you bought here at $100 a share. You sold here at $200 a share. And no matter what the stock did in between here and here, you still made $100 a share, or you doubled your money. So it doesn't matter if the stock went straight up from 100 to 200, or if what really happens in reality, it goes up and it goes down and it goes up and it goes down and it goes up and it goes down, and eventually you still sold at 200, you still made your double, or you doubled your money. Okay, one last one. Example number 6. So F is going to be the vector field, and F is equal to x squared times y, and y divided by x is F, capital F, is capital F conservative? In other words, does capital F equal the gradient of something? Question. Well, if so, then take the derivative of f with respect to x and you'll get this. Take the derivative of f with respect to y and you'll get this. So in other words, is there some function that the derivative with respect to x is equal to x squared times y? Well, if so, the antiderivative of that would be x cubed over 3 times y plus some constant. And the derivative with respect to y equals y over x. And then find the antiderivative of this, which is going to be y squared over 2, and the x just stays there. So, like I said before, this is a constant, but that means that this might have some variables in it, but we'd be holding them constant. So what you do now is put the two parts together. It's not saying that the two parts have to agree, you just put the two parts together. So then f definitely has to have an x cubed over 3 times y, plus it has to have y squared over 2x, plus it could have an actual constant like 17. And then you need to check the answer. Check it. Dun, dun, dun. Okay, that's a different party. So take the derivative with respect to x. So this will be 3x squared, and then the 3's will cancel, so it leaves x squared times y. And because we're taking the derivative with respect to x, you have to take the derivative here. So I would just look at this as 1 over x. Its derivative will be negative 1 over x squared. And then the 2 will just stay there, and the y squared will stay there. And then, does this match this? Well, the first part does, but the second part does not. And so the answer is no, that did not work. So you not only need to do the antiderivatives, you then need to put them together as one answer, and then you have to check it and make sure that it's right. In this case, no, it's not conservative. So if it's not conservative, you can't just go straight across. You do actually have to integrate along this whole red curve.